Okay, so for the most part, whenever you get some sort of Boolean function, you're going to be given to it's going to be given to you in the form of a truth table, right? So a truth table is just a really easy way to specify how one of these Boolean functions work, because you can literally just say if these three things or these four things or however many things are your inputs, like if A is 1, B is 0, C is 1, then the output is going to be 0 or whatever it is, right? It's very, very easy to take a truth table or to make a truth table for any given behavior that you want. So the ultimate goal, though, is not to just have this truth table we write down somewhere. The goal is to have a circuit that we can physically build somewhere, right? And in order to do that, really what we want to be able to do is just draw the circuit, and then that's a representation of what you could physically build. So our goal here is to make a circuit. It's to make a physical thing that can actually do the function, right? You could actually give it inputs, and it will automatically produce the output on its own without any work from you. So how can we do this? How can we go from a truth table to a circuit? Well, the first path, and this is what you practice on Tuesday, the first path is first just doing sum of products, right? And at least with the example of XOR, you can just go directly to a circuit from here. Typically, though, if you're going this route, you're going to want to manually minimize using Boolean algebra or something along those lines. Not a K-map in this sense, in this context, because you've already come up with an equation. At this point, you would just use Boolean algebra or something to simplify. The second route is to use a K-map, right? So you could also go from a truth table, use a K-map to get to a minimized equation. So you can sort of see here that the equation that you get out of minimizing sum of products and the equation that you should be getting out of K-maps should essentially look the same. With minimization manually from sum of products, you can usually do a little bit more tricks and maybe get something that looks more simplified. But for the most part, we're not too picky on that sort of minimization. If you do a K-map and you do it properly and you extract value from it, you should just get a nice minimized value that you can just immediately make a circuit out of, right? So I'll be talking about this process here. But yeah, the idea is you take a truth table, you put it into a K-map, then you extract the minimized equation from that, and then you can make a circuit out of it. Then you have a third option here. Implementation with a mux. By using a mux, you can go straight from the truth table to a circuit without having to come up with any equations, without having to do a K-map, without having to do sum of products, without having to do Boolean minimization, anything like that. You go straight from the table to a physical circuit that you can build, right? And in terms of simplicity, this is probably the easiest option. And as I work through, if you're not super comfortable on doing this, hopefully you will after this review. But yeah, this is sort of the main idea. These are the three routes that you might end up taking, going from a truth table to a circuit. And typically, on a sort of test or something, you'll be asked to do a specific one of these, right? Maybe you'll be given a truth table and asked to give sum of products, or given a truth table, get the K-map, get the minimized equation, and then build a circuit, or just given a truth table, implement with the multiplexer, right? So something to notice is if you're doing sum of products, you're not doing K-maps or muxes. If you're doing a K-map, you're not doing sum of products or muxes. And if you're doing a mux, you're not doing a K-map or sum of products. So just keep that in mind. It's going to pretty much always be one of these three. Any questions on this before I move on and start taking a look at K-maps? Okay. So let's just start with some arbitrary, go for A, B, C. And then for Q, just for practical purposes, I'll just put some random sort of function together. Okay. So actually, I'll put a 1 here. Why not? So for k-maps, what you want to do is you want to look at, see how many variables you have, and that's essentially how many variables you'll have to end up putting in the k-map. So it does not matter in what order you label these, right? You could put BC up there and A down here. This is just one of the ways that you can do it. Whatever you end up doing, the k-map will end up being correct as long as you do it properly. But your k-map might look a little bit different, but it's essentially the same thing regardless of how these are labeled. So now we go ahead and make the grid. And then we need to label the possible options for A, B, and C. Well, C, obviously it can be a 0 or a 1. A, B together could be 0, 0, 0, 1, 1, 0, or 1, 1. But the problem is that we can't just put these here in any arbitrary order. You need to do it essentially where if you're going from one to the next, you're only changing one bit. So here we have 0, 0. Then we'll change this 0 to a 1 to get to this one. But here, you notice if we put this value next, we have to change this 0 to a 1 and this 1 to a 0. And that's not valid. You can only do one of those changes. You can technically there's multiple different options for what you can put up here. The easiest one that you'll probably see, and that is in the slides, is this one, right? So going from here to here, we change this bit. Going from here to here, we change this 0 to a 1. Going from here to here, we change this 1 to a 0. And then going from here all the way back, we're changing this one to a 0, right? You should have learned in the class that these sort of k-maps do wrap around, which is a little bit complicated to work with at the beginning, but it's generally not too complicated as you get more used to it. So now what we want to do is we want to take this table and put it into the k-map, right? Exactly as it is. I typically just ignore the zeros for putting it into the k-map. It just adds clutter into the k-map, and so I'll just look at the ones and put those in. So for this one right here, let's see. For this one right here, we see that A is 0, B is 0, right? So that's this column right here, and C is 1, which is right here. So this one should go right here. Then you have a 1 right here. A is 0, B is 1, that corresponds to that column, and C is 0, which corresponds to this row, so that one goes here. Over here you have A is 1, B is 0, that is this column here, right? Because A is the first digit, B is the second, and C is 0, so that's this right here. And we've got, let's say that. That's also 1, 0, but the other row this time, right? 1, 0, 1. And then finally, we've got this last one here, which is 1, 1, 1. So that's 1, 1, and 1. So that goes right here. Any questions on how to take a truth table and then put it into a k-map? And also just there's zeros everywhere else technically, but I'll just leave them out. Okay, so now comes the part of k-maps that is sort of like a game. What you want to do is, it's sort of like a Sudoku or something like that. It's not too crazy difficult, and there's a pretty good strategy for going about doing it. So what you want to do for this strategy is you'll start with to try to make the biggest possible circle that you can. So in this case, there's 8 possible grids. So we'll just say, okay, well, what if we, let's see here. I don't know, I'll use that. What if we just circle all of these together? Right? Well, the only time that we can circle things together is if there's ones in every single one of these boxes, right? But which there isn't. So we cannot make a circle of 8. And because we failed at level 8, we'll go down to the next box size, which is 4. And the boxes need to be sizes of powers of 2. So you can have a circle or box of size 1, size 2, size 4, 8, 16, 32, 64, and so on, depending on how big your K-map is, but we generally won't go above 4. You might see an example with 5. So yeah, we'll go down to 4, and we'll see if we can circle anything 4. The rule for your circles, or for how you can box things together, is they must be rectangles, keeping in mind that a square is also a rectangle. So you can do this, you can do this, you can even wrap around, as you should have seen in lecture, but you can't do something like this, right? Because that's not a rectangle. You can't just circle 2 diagonally like that. That doesn't work. If you try to get an expression for that, it wouldn't be valid. You wouldn't be able to. So yeah, we'll look for 4. Can we circle anything in a circle of 4? There is no rectangle full of 1s, so no, we can't. So that fails. We'll go down to 2. So now with 2, what you want to do is you want to look at any, and with 2 and with any other thing, you really want to look at everywhere you can see a 1 and see if you can include it in a circle of that size. So if I go right here and I look at all of the adjacent blocks, right, which is just going to be down, this block, this block, this block, I can't make a circle of 2 with it because there's no adjacent 1s. Okay, so we can't do that for this one. Can we circle, let's say this one in a circle of 2? Yes, but there's more than one option, right? So we could circle these 2 together, we could circle these 2 together, or we could even circle these 2 together, right? And because of that, I'm not going to do anything for that one just yet. What you want to do is you want to look at, let's say, this one here. This one here can only be circled with this one. It's not possible to circle this purple one with anything else. And you ideally want everything to be in as large of a circle as you possibly can make it. So because this is the only option, this has to be a circle in the final solution. In whatever your K-map ends up looking like, this circle has to be there, because otherwise it wouldn't be as minimized as you possibly could make it. Okay, so now that you've circled this one, you don't need to look at it anymore. But we can then look at this green one here. So this green one, can we circle it with any other one around it? You might say no, but the answer is yes. You can circle it with this yellow one here. There is no, you can overlap circles. There's no problem. That'll actually end up with a more minimized equation. The only thing that you shouldn't do is circle, like, let's say there was another, I don't know, let's say there was a 1 here, and I already circled these 2 together. I wouldn't want to circle these 2 together because that's just a redundant circle. Both of these 1s are already in a circle, so there's no point in circling as well. But here, because this green now is in a circle of size 2, this circle here is worth it because it's going to help minimize the equation. So now we can look at this 1 here. We can circle it with this yellow. So we did end up doing all 3 of those circles, but you might not have immediately seen that if you were just trying to see what you could circle with a 1. So the general rule is look for 1s that can only be circled in one way at a given size. And if so, circle that, right? And then you only want to look at uncircled 1s for circling anything new. So we've already circled all of these, so I would only look here to see if I can put it in a circle of 2, and I can't. So that means I would go down another size. So from size 2 to size 1, well, obviously I can circle that alone, and this is what the bubbles for your K-map would be. So now you want to come up with the min terms for it. So I'll just do this first one here. So here we can see that in this bubble, A is always 0, so we can put a not A. B is always 1, so we can put a B, and C is always 0, so we can put a not C. Okay, so then we can go to a different bubble. Let's say this one right here, this vertical one. So now we can see that A is in this bubble, right? What we can do is look at this column and these 2 rows, because that's where that's the column and rows that bubble occupies. We can start just with the columns. We can see that in all of the column this bubble occupies, A is always 1. So we know that A is going to be in our term. B is always 0. So we also include it. But C is 0 and 1 inside of this bubble, right? So we would have to put C, or we would have to put not C, but because both of the options are inside of this bubble, we're going to leave it out. And that's how you get the min term for these bubbles without having to do any sort of algebra after the fact. Okay, so now we'll do this bubble here. This one, as you can see, occupies this row and these two columns, right? So in these two columns, we see that A is 1 in both. So A is going to appear in this. B, however, changes, so we're going to leave it out. And C is always a 1, so there's going to be a C in there. And then lastly, we've got this bubble here, which, keep in mind, is circled with this 1 over here. So this bubble here occupies this column, and this row. So if we, again, look, we can see that A is 0 here and 1 here, so we're not going to include it. B is 0 in both, so we'll put a not B for our term. And C is 1, so we'll put just a C. And this means, now that you've collected all your terms, now you just OR them all together. So Q equals not BC, or not A, B not C, or AC, or A not B. And that's your minimized equation. I'll probably go through another example just to sort of cover different scenarios that you can get with K-maps. But is there any questions on this? All right, sounds good. I'll go ahead and move on to another example. I guess I'll have to erase some stuff. Okay, so let's just choose a different function now. Let me try to come up with a particular example here. We'll say this. Okay, so again, we want to draw our K-map. So AB up here, C down here. And again, the order of these labels matters. If you label them like this, then you will get the wrong answer. The equation that you will end up with will not work. Sorry, I was on the wrong channel. I did not see questions. Let me see here. I can, well, which of the examples from the lecture practice problems, or are you talking about the practice problems that were handed out? Okay. Let's see. I probably won't cover it. If you would like to check your answer, you with me or with anyone, feel free to post what you get. But maybe if I have time, maybe if I get through all of the stuff that I want to get through with quickly enough, I can take a look at that. Okay, so I'll do this a little bit more quickly, putting the ones in. So one of the reasons that I like putting, like you see A, B here are the leftmost ones, and I put them on top. The reason is because the sort of way that I think about putting these ones into... no, these can be whatever you want. These can be whatever you want. These have to be pretty precise, otherwise it won't work. Here you could even put BA and then C, or you could put CA and then B. I typically prefer putting AB on top of here because it makes it seems to be, for me, it's easier to transfer the table into the K-map if AB is up here. Because what I do is I say, okay, well, there's a 1 here, right? Well, it's 0, 0, which is this column, and then 0, which is this row, so there's a 1 here. So it sort of makes it easier. You can read what AB is, see what column it is, and then read C, and then put it in that row. It's a little bit, I don't know, maybe something's easier for you. It doesn't really matter as long as you transfer the table into the K-map correctly. It's fine. So yeah, so 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, or yeah, sorry, 0, 1, 1, and then we have 1, 0, 0, and 1, 0, 1, right? So should be able to see that this is how you put all the ones into the K-map. So now to do the minimization. So again, we'll start with circles of size 8 because that's the maximum size. Clearly there aren't 8 ones, so we can't do that. Then we go down to a circle of 4. Can we circle any of these ones here in a circle of 4? The answer is yes, because we can do this whole wrapping around. So if we, or rectangle of 4 if you'd prefer. Because we can wrap around. In reality, we're sort of drawing this out as a table because we're on paper, or in this case a screen, so it's easier to work in 2 dimensions. But typically K-maps are actually not really supposed to just be done on a table. They're supposed to be like, you're supposed to program them or something, and so you end up with this weird artifact when you draw them that you have to do the wrapping around. But if you notice here, right, going from this bit to this bit changes by 1. Just like going from this one to this one, this bit changes from a 0 to a 1, right? And really you want to think of these columns or these rows being next to each other if they change by 1 bit. So that's why that you can wrap around, is because these are, if you sort of shift all these over, like if I would have labeled these 0, 1, 1, 1, 1, 0, 0, 0, which is also a valid labeling, because again, it changes only 1 bit changes from one column to the next, you would see that these 2 columns here would actually be next to each other. Right? So if they're next to each other, they can be circled. So yeah, so we end up with all of this. And now we're still at this like level 4. We're trying to create these circles of 4 ones. So we've already circled all of these, so we'll ignore them for now. And we want to see if we can circle this one in a circle of 4, or a rectangle of 4. We can't, unfortunately. You might think, oh, well, we can maybe circle these together, but that's 3. That's not big enough. These boxes need to be of size power of 2. You can't sort of bend in like an L shape or anything like that. So we can't circle this in any circle of 4. So we go down to 2. At level 2, however, we can circle this one with this one here. Again, overlap doesn't matter as long as you're using the overlap to circle an uncircled one, and make it more minimized. So here now all the ones are circled, so we're done. Right? And adding any extra circles would just be redundant, and you just end up with extra terms in your equation. And I see people writing questions, so I'll wait till they post them. So the answer is just pretty much how K-maps work. So well, let me just quickly get the term for this bubble here, and then I'll explain why that's the term and why that works. So so here we can see that it occupies this column, and this row. So we see A is always 0, so we'll put not A. We see B changes, so we'll leave it out. And we see C is 1, so we'll put C. So the term for this bubble here is C. Now, why is that? Well, if we look at the individual terms here, so if you look at the term for this one and this one, the term for this one is not A, not B, C. And the term for this one here is not A, B, C. And really, if you were to just do sum of products, you would end up with this right here. And, well, if you were to do Boolean algebra, what you could do is you could factor out this not A, C from both terms, right? And then you'd end up with not B plus B. And then this right here, let's see. Yes, I will be going over that at some point, or probably when I get closer to. I'll do it between this and Muxes, but yeah, I was planning on doing that. So yeah, so here you have not B or B. Well, there's a lot of rules about Boolean algebra that you can do. If you don't remember one, just plug in 0 and 1, right? There's 2 options. It's not really that many cases to work out on your own, and you can figure out some of these less intuitive properties just by doing that. So if B is 0 here, then it'll be 1 plus 0, which is 1, right? And if b is 1, then not b is going to be 0. B will be 1. 0 plus 1 is 1. So this right here is always 1, and it disappears, right? So you end up with that this is equal to not AC 1, but anything and 1 is just not AC. Now, the reason that you were able to do this cancellation is because you had both the not B and the B term. If you didn't have both of those, then you wouldn't have been able to do this cancellation. And that's why your boxes need to be rectangles that are aligned to the axis, because two adjacent boxes in a K-map have at least one term here that can be canceled out in exactly this manner. But instead of having to do it with Boolean algebra and having to figure out how you should look at this, you do it by circling things, which is a lot easier for you to do than to actually try and, figure out what terms are. And the fact that this one here is circled twice means that you actually would have had to do a weird trick where you just duplicate the term in order to actually be able to minimize, which is also very difficult to see when you should be doing that. But in a K-map, it just ends up looking like you circled it twice, which is super easy. In the case of these four over here, this has all combinations of, let's say, A and B. So you have essentially, I'll put the B in front here. So you have B times AC or A not C or not AC or not A not C, right? This red circle around here, or sorry, this should be not B here. If you just wrote out all these min terms and then factored out the not B, you would end up with this. And if you sort of work out through all the cancellations, this ends up being 1. And the only reason that's the case is because all the ones are next to each other, and you have all four of these possible options, right? Because this could be just itself, or it could be the not version. This could be itself or the not version. There's 2 options for this, 2 options for this. So there's 4 options total. And for 3 variables, it's 8 options. So that's why you get these powers of 2. And why these boxes have to be powers of 2 is because you need to have all the correct terms to cancel out in order to be able to circle the ones together in the K-map. Does that answer your question? Okay, well, yeah, so I'll just keep working on the K-map. Okay, perfect. So it's a little bit cluttered here. Let me remove some of this stuff. All right, so just to make it clear, all of this sort of Boolean algebra that I was doing was just sort of as an explanation. You really should not be doing any Boolean algebra if you're doing a K-map. That sort of defeats the purpose. The point of the K-map is that you can just do the K-map, circle some stuff, and immediately get the terms out of it. So again, we have this not AC coming out of these two, and out of this one, we can see that B is always 0. Or sorry, A. Well, I'll start with A. Again, this circle here occupies these 2 columns and these 2 rows. So we'll look at A. A changes in the column, so we won't include it. B is always 0, so we end up with not B. And C changes, so we won't include it. And so our ultimate equation for this table here is Q equals not AC or not B. Any questions on this? Would anyone, or would people like me to do another K-map example? No, K-maps never give an XOR. That is, so let me just erase some of this stuff here. It'll be a little bit cluttered. You can, in theory, see when you have it. Let's see. The biggest mistake I have ever seen is mislabeling this stuff here. As long as you do that and you just are careful to transfer over the truth table into the K-map, that's good. The other mistakes that I see are circling things that aren't powers of 2 or aren't rectangular. So like early on, I'll see people circle things like this or circle 3 things together. As long as you don't do that, the worst thing that you can do is accidentally not minimize as much as you would have wanted to. So let me, 1 second here. Okay. This is the wrong channel. Give me a second. And there we go. And then for K-map, for XOR, if you ever end up with sort of an XOR situation, you'll end up with 2 ones that are diagonal from each other. So actually, if I draw this, you sort of will end up with 2 boxes diagonal each other. If you see this equation here is not AC, and this one right here is A not C. And if you remember from the lab, the sum of products that you should have gotten is exactly this, which is A XOR C. And because it's sort of diagonal and you're not really allowed to circle diagonal things together, you should never get an XOR out of the minimized equation from a K-map. All you'll end up with is ands, ors, and nots. And like if you do see this situation or something, don't put A XOR C, just write this down. XOR is sort of seen as like a little bit more of a complicated gate than and, or, and not. So when we really say minimized equation, really what we're talking about is something that just looks like a sum of products, and a minimized sum of products at that. Okay, so see someone else typing something, so I'll wait for them to do so. Okay, so again, I might go over another example for K-maps, maybe that one example that someone posted. But for now, I'll go ahead and move on just so that we can get through all of this stuff. So the next thing that I'm going to do is cover something that you'll have to do in the lab. It's not all that different from what you've done already, but it might look a little bit different. So let's say I have a truth table like this. And the inputs to this function here are going to be A, B, and C. There's also going to be a C in here, but I'm just not going to write it in one of the columns. What I'm going to do instead is be able to say that Q can possibly be C, right? So I'll say that when A is 0 and B is 0, Q is just going to be whatever C is. Or I could say that Q here is just going to be 0, right? If A is 0 and B is 1, then Q is just going to be 0. I could even, put a not D here. I could put whatever I want really in this column to specify what the function's doing. And the sort of problem here, I can put maybe a not C here. So the problem here is, how do you get an equation out of this, right? This sort of doesn't follow the same sort of rules as a normal truth table. You can't really do sum of products, but it turns out that there's something very, very similar to sum of products that you can actually do. Let me just replace this here with actual just ones and zeros and show you one of the ways that you can actually think of sum of products. So instead of just going to the rows where there's a 1, I'm going to come up with a term for every single one of them, but we'll see that the terms for these 2 rows here will just end up disappearing. So what you actually want to do here, for the term for this row, what you have is A is 0, so we'll put a not A, B is 0, not B. That's the exact same thing that you've been doing, except now what I'm going to do is I'm going to take this thing and also AND it. So I'm going to also AND this term with 1. What that's going to do now is, well, if you simplify this, anything and 1 is just going to become not AB, or not A, not B, right? So that's this first term. For this one here, we have not A, B, and then 0, because there's a 0 here. But 0 and anything is just 0, so this term disappears. For here, we have A is 1, B is 0, so we can actually write A, not B, 1, and that ends up just being A, not B, because anything and 1 is just whatever that other stuff is. And then for this last one here, we have a, b, 0, which again is just 0 because 0 and anything is just 0. And so now if you just OR all these terms together, and really we can ignore these zeros because they don't matter, you're going to get the exact same equation that you would have done for sum of products. Well, now let's just change this a little bit, right? Instead of having only zeros and ones here, let's just put a C. Well, now all we have to do is we have to change this 1 to a C, and we have to change this 0 to a not C. And now this just stays not A, not B, C. This one still becomes 0. This one still just becomes A, not B. And this one will just become A, B, not C. And then you just OR those together. Right, and I've written the 0 here, but you don't need to include it because 0 or anything is just the anything, right? So this is a way that you can go from these truth tables that have variables in them to an equation. Now the reason that I even introduced these types of functions here is because it's generally easier to talk about the truth table for a multiplexer using those types of tables. So here, let's look at a 1 var mux. So 1 var means there's one selector line, so I'll just have S0 here, and then I'll have Q. And so the truth table for a 1 var mux is when S is 0, we're just going to output I0. And when S0 is 1, we'll just output I1. Right? And so part of the lab is going to be taking the truth table for a 2 variable mux and doing that exact same process to come up with an equation for it. Typically that equation wouldn't be minimized, but for the case of a 2 variable mux, it will be minimized. So you end up with a really easy way to come up with a nice equation for a mux. And so the best way I think to think about a mux is just you read the S inputs as a binary number and you just output I whatever that binary number is. So that's not super clear with a 1 variable mux, but if we go to the 2 variable mux, right, we have S1, S0, Q. Notice how I'm writing these in decreasing order. The reason is because when you're reading in binary, right, this is the 2 to the power of 0's place, then 2 to the power of 1, 2 to the power of 2, right? Like if we have this number here, you start with 0 on the right and move upwards this way. And we're going to do the exact same thing in tables whenever we have like a sequence of S inputs that represents a single number. So here, if you do 0, 0, 0, 1, 1, 0, 1, 1, so now you can just read this binary number. What is 0, 0 in binary? It's just 0. So Q is going to be I, 0. 0, 1, that's 1 in binary. So we'll output I, 1. 1, 0 is 2 in binary. So we'll output I, 2. 1, 1 is 3. So we'll output I, 3. And this works for any number, any variable mux, right? You just essentially will continue adding on. Like if I want to go to 3 variable mux, I'll just add an S2 here. I'll just have to put zeros here, and then ones here. Right, this is 4 in binary, so this will be I4, then I5, I6, and I7. That's really it. That's the entire thing. That's exactly how a mux works. And if you can remember that, it's relatively simple. And what you'll see we end up using muxes for is sort of selecting things, right? What you want to think of this as is we have 8 options here, and we want to choose one of those options, right? And to do so, we'll just pass in a number into the S input and say, hey, I want option number 4. And that way, I4 is the thing going to be output into Q. And it allows you to essentially go from having multiple things and combining them into one, not just by like, ORing everything together, but by only letting one of those through. So any questions on it's technically the 5th option, but because we start at 0, it's option number 4. So we'll have we have option 0, 1, 2, 3, 4, even though that's the 5th on the list. It's just because we end up counting from 0 for most things in this course. Any other questions on just how a mux works before I move on? And I'll start looking at how to implement functions with multiplexers. And also just a quick note while people are writing their questions. If you were to write out the full truth table, the full truth table for this, it would have 1, 2, 3 columns, right? And well, if you have 3 inputs, that means 2 to the power of 3 rows in your truth table, right? So that's 8 rows. If I looked at this 3 variable mux here, we have 3 plus 8 inputs. That is 11 inputs, which means there's 2 to the power of 11 rows, which means there would be 2,048 rows. So someone said this seems like the opposite of minimization. This isn't really minimization. It's just an alternate way to represent the truth table. The thing is that if I was actually to write out the full truth table for a 3 variable mux, it would take up 248 rows, which is absolutely insane. I'm definitely not going to have the time to write all of that out in a lab period. So this is basically the whole truth table, right? But I've sort of taken a shortcut in writing I0 here. If you put all of these inputs up here and then just put zeros or ones for Qs, you would just end up with an absolutely massive truth table that's impossible to handle. So this truth table just allows you to at least know the truth table of a mux without actually having to write out this ridiculously large truth table. It's essentially equivalent. Like you can, this is a sort of a minimization of the normal truth table for a 1 var or 2 var or 3 var mux. It's just written in a way that I think is a little bit easier to understand. The inputs are whatever you want them to be. Yeah, these I inputs are inputs. It's like the A and B inputs of an AND gate or anything like that. It's literally a circuit, right? I could draw a, let me make some room here. I could draw, let's say I'll just draw a 2 var mux, right? So it just has 4 inputs or 4 data inputs and then 2 selector inputs and then the output Q, right? You can pass in whatever you want. This is just like an AND gate. It just has a lot more inputs. An AND gate or XOR gate or whatever, it just has more inputs. To quickly answer Juan's question, whenever you see an equation like this, right here, let's see, not A, not B, C, or not A, B, this is the output. An equation can only ever have one output. If you want to make a circuit that has multiple outputs, you just need to make multiple circuits and put them into the same circuit. These are all the inputs. A, B, and C are all the inputs, and Q is the output. It's right here. Oh, are you talking about the full truth table? Okay, let me just go ahead and clear this because it's starting to get cluttered. Yeah, so yeah. Okay, so I'll go ahead and do the 2 var. Quickly answer Christopher's question. The trapezoid is the technical shape of a multiplexer, but like for drawing on like PowerPoint or something, it's just kind of tedious to actually draw the rectangle, to draw the trapezoid, and so you can just draw a rectangle as long as you say it's a mux. Like if I draw a trapezoid shape, you can assume that that's a mux. If I draw a box, I probably need to say, hey, this is a mux. Either of these is valid, right? As long as you're making it clear what you're talking about, it doesn't really matter what notation you use, though you should use what's canonical. If it's easier in whatever circumstance you're in to just draw the rectangle, just make sure it's clear that to whoever you're showing it to that it's a mux. Otherwise, you can use the trapezoid, and then that should be the mux. So just really quickly, this was the truth table that I had shown for a mux, and then this is going to be the full truth table here. Okay. So again, the rule for a mux is you look at S0, depending on what it is, that's what the output will be, whatever I0 is. So here, S0 is 0, so we'll output whatever I0 is, which is 0. S0 is 0, so we'll output I0. S0 is 0, so we'll output I0. S0 is 0, so we'll output I0. S0 is 1, so we'll output I1. S0 is 1, output I1, output I1, output I1. So you can see for all of these here, right? This is the case that S0 is equal to 0. The output is just I0. And in this case, S0 is 1 and Q is I1, right? So this is literally just a much more verbose way of saying the exact same thing, right? If you look at the table explicitly, you can see that the reason this is a 1 here is because of there. This one comes from here. This one comes from here. This one comes from here. And really, the zeros come from there as well, right? So this output here is because this is what the input is here, and this output here is because this is what the input is here. Let me erase this so you can see a little bit better. Does this help to clear it up a little bit? Yeah, it's a little weird, but yeah, as the main reason I introduced this is just because, you know, even for the 2 variable mux, which is what you'll be making, you know, if you were going to do a k-map with a 2 variable mux, it has 6 inputs, and doing a 6 variable k-map requires you to do some really, really weird stuff. And so it's not really possible for you to do a k-map with that. The sum of products output of the full table for a 2 variable mux is also very unwieldy. And so this is going to end up making your life a lot easier when you actually get to working on the lab. Okay, though. So now we can go ahead and start with looking at how to take a function and or take a truth table and then just make a circuit out of it directly without going through k-maps or anything like that. You're just going to go from a truth table to a circuit and you're done. And it's going to be, it is surprisingly easy. So I'll start with a little bit of an easier example here, and I'll be using 2 variable muxes because it's a little bit more complex, but it's not too complex that it's just tedious to work through. And this should also help quite a bit with understanding how a mux works. So let's say I've got, I don't know, XOR. We'll do XOR. And we'll start, as I said, with a 2 variable mux. So when you're solving these mux problems, whenever you're trying to go from a truth table to a direct implementation with a multiplexer, the first thing that you need to do is choose what your selector lines are going to be. Now it might not be obvious why this is the case, but hopefully as I'm working through it, it'll be obvious why. But essentially, the way that you might have come up with that on your own is, you know, maybe you just had a multiplexer lying around. I don't know. You have a breadboard and a multiplexer, and then you just started playing around, you know, passing inputs in, and you figure it out. You know, if I pass A and B into here, then it's really, really easy to figure out what I need to input here in order for this output to match this output. Okay. And just to, if you're wondering why, I'm like, the question that you'll see here will be implement this function with a one variable mux. I'll get to that. I'm just going to start with this because it's quite a bit easier to do it with the two variable mux. So now that we've chosen our options for A and B here, what you want to do is you want to just go through all the possible options for what A and B could possibly be. So we'll just start with 0, 0, right? We'll say that A is 0 and B is 0. So if I look at the truth table here, I want Q to be 0. So I want the output here to be 0. But I somehow need to pass in something to one of these inputs so that that's true. Well, if I pass A and B here as S1 and S0, then I'm passing in 0, 0. And if you remember, I'll go ahead and write down the truth table for a mux, or two var mux. So again, if you're passing in 0, 0 into the multiplexer, the output Q is going to just be I0. It's whatever I0 is. So if we want the output to be 0, we have to pass in a 0 here, right? In order for this mux, in order for what we're passing into this mux to act like this table, right? Okay, so now we can move on to 0, 1. So when it's 0, 1, we want the output Q to be a 1, right? Just according to what this table is saying. This is what we want it to do. But right now, this is what it's doing, right? This is what it's doing. So, well, if we want the output to be a 1, and passing in 0, 1 into the mux selects this, corresponds to this row, which means it's going to take I1 and output it. Well, this I1 had to have been a 1 in the first place in order for this one to be the output. And, well, you can notice the striking similarity between these two tables, right? In this one, I just have actually 0, 1, 1, and 0. But here I have variables. I have placeholders. So why don't I just take all of these and set these to those? If I do that, then, well, if I pass in A and B as S1 and S0, right, because A corresponds to S1 in this table and B corresponds to S0, then you've just implemented the function, right? And you've done literally no work. You've looked at your truth table, you've taken this column and you've passed them in as all the inputs to the multiplexer, and boom, you have a circuit. You did essentially no work, right? Obviously, you had to have acquired some sort of mux beforehand, but this right here is literally an implementation of this function. You didn't have to go and get a sum of min-terms formula. You didn't have to do a k-map, nothing like that. You just went straight from truth table to circuit. And at least for whenever the number of variables in your mux matches the number of variables in your function, it's always going to be like this. You can just pass in all of your variables into the selector lines and then just basically put what you want the function to output in these locations, and then it just does. It just outputs those. Plain and simple. Any questions on this before I move on to implementing it with a smaller mux? Well, I mean, you'll be making a 2var mux. They're very simple to make, but essentially what's going on here is it's exactly the way this table is laid out is that you've essentially just said, well, instead of actually giving specific outputs, let's see. Yeah, well, so this is. Let me say one thing, and then I'll answer your question, Tom, or your comment. Respond to your comment. So this truth table here essentially, for the mux, essentially looks like just any arbitrary truth table you might possibly want to make, right? Here, instead of having a 0, 1, you just have some variable you called I0, and you have some variable you called I1, right? If you set those to anything in particular, you end up with literally any truth table you could possibly want, right? It really is sort of a very easy way to describe a completely universal logic gate. So it's really it sort of is magic, right? A multiplexer is defined to sort of just be this thing that is completely universal, and you can implement whatever you want with it. What do you mean by combine I1 and I2? Here, yeah, typically if you're on a test, yeah, you would combine. Sorry, if you're on a test, you just need to write down what I had here, because just writing out all the lines would be complicated. Really, what you would end up doing if you're actually making the circuit, right, is you would take these two, you'd combine these together, you'd somehow send a 0 here, and then these two here would be connected, and then you'd somehow send a 1 here, or maybe I have a NOT gate, right? But typically on a test or something, we won't ask you to do this because it's harder for us to grade, right? If you're asked to do this on a test, literally just write all the lines and then write what it needs to be. That way we can easily look at it and easily grade it. Okay, so Tom's comment was, it looks like you're passing Q into an input to get Q out. Well, the thing is, you want to think about these two things as two things. This is a truth table. It's some random thing. It's some random thing that I wrote down. I can't physically make this truth table, at least not immediately. It's not. It doesn't physically exist. This right here does, at least in theory, physically exist. I could go out to the store right now, buy a multiplexer chip, get a breadboard, put the chip in, put some switches on the board that are labeled A and B, pass in zeros and ones into these inputs, and then magically I've implemented this truth table in reality as an actual physical function that works, as a physical circuit that works, right? And so, yeah, essentially you are passing what you want to be the output as the input of the mux. But the thing is that you don't have this output automatically somewhere, right? It's just written on this truth table somewhere, and you can't actually run it. There's no way to actually simulate this, but you can simulate this. You can run this. It's a physical circuit that can be run. So yeah, you essentially are just taking the output, passing it into the input so that this output matches this. Any other questions or comments before I move on to using a smaller mux? I do see someone typing a question, so I'll wait for them to finish. Yeah, pretty much like a mux is a blank slate. It's a way to essentially almost create a circuit just by specifying a truth table without really any much more work. So yeah, the output Q isn't necessarily supposed to always be true. It's supposed to be whatever you want it to be. In this case, we want it to be this, so we set the inputs up to the mux so that the output is this. Okay, let's see. I'll go ahead and start by doing this example over again, but with a one variable mux. So now we're going to do this with a one variable mux, and then I'll also do an example of a truth table, a 3 input truth table, and implementing it with a 2 variable mux. So here we're only going to have S0, we have I0, I1, and again, just to write it out really quickly. That is the truth table, and now we want to implement this function. So now our job gets a little bit harder, but it's still not too bad. So again, the first step, the absolute first step you should always do is choose what you want the selector lines to be. Otherwise, you have no cases to consider. Right? You can't say, okay, well, what if A and B are both 0, right? You have nothing to consider, right? You have to choose what your selector lines are first. For this one, I'm going to choose, let's say, A. And the reason for that is because it's on the left, right? And I'll point out why it's useful as I'm solving. So the first thing that we're going to consider is what happens when A is 0. Right? So when A is 0, well, now if we look at the truth table, there's 2 rows that correspond to A being 0. So you can't just like put a 0 or a 1 here necessarily, right? You're going to need to think about it a little bit more. So we've used A already over here. So we're going to sort of ignore this A column for now. let's just split it here, right? So what you really want to be doing is considering this block here. So now, is there any way that you can express what Q is in terms of B just for these two rows, right? Let me just, no, that's not the right color. So yeah, if I sort of just scribble these out, can anybody tell me, just looking at this blocks, Q is clearly the same thing as B, right? Here, when B is 0, Q is 0, and when B is 1, Q is 1, right? So when A is 0, Q is B. So because of that, let me erase this. Because of that, we're going to put a B here, right? And this is essentially what we're getting at with the mux. And when the multiplexer has the same number of variables as inputs to your function, it's just this trivial thing. But really what you can do with these multiplexers is you can sort of break your truth table down into a bunch of cases and then figure out an equation for each of the cases separately. And that's going to be a lot easier, right? It's pretty easy to see what this equation is just for these two rows, right? Figuring out what the entire equation is isn't as obvious. But for these two rows, it's a lot easier. So when A is 0, in these two rows, we can see that Q is always the same thing as B. So we can put a B here, right? So now when A is 1, and again, I put this over here because we're passing in 0 to the mux, so it's going to be selecting I0. So if we want the output to be a B when A is 0, then we need to put a B here at I0, so that's what gets passed through. So now for A is 1, well, yeah, so as someone posted in the chat, here we can look, when A is 1, B is Q is exactly not B. It's exactly the opposite of B, because here when B is 0, Q is 1. When B is 1, Q is 0. So for I1 here, we can put not B. And this will be Q. This will be the proper output of our function, right? And there we go. Now we've taken this table and we've implemented it with a smaller mux, which means it's even cheaper to make. We did technically use a NOT gate here, but that's allowed, right? Whenever you're doing this, you'll either end up putting B, not B, 0, or 1, or maybe it's a different variable. But these are your only 4 options for what you'll put in as an input when the size of your multiplexer is 1 less than the number of inputs. I'll go over another example like this afterwards, so don't worry too much if it's not immediately clicking. But yeah, if you have any questions on this, go ahead and ask them. The answer to your question, Michael, is technically no. I mean, I used a 2 variable mux to implement this. I could also use a no variable mux, right? I could just pass in A XOR B, right? A 0 variable mux is just nothing, right? So I could just pass an A XOR B into the I0 input of my no variable mux, and that would just be the output Q. Or I could use more variables in the mux. Typically, however, what you will be asked to do is with n inputs, you'll need to use an n-1 var mux. That's really the case that we're worried about for the most part. So let's see here. Yeah, so I'm being a little bit purposely vague because the answer is really nuanced. I will post a document that talks about implementing functions with multiplexers that can probably answer that question a little bit more specifically, but I don't want to confuse anyone, so I'm not going to answer it completely. let's see. So the next question is, does S0 always correspond to A in examples like these? No. Remember, the first step is to choose what you want S0 to be. I can choose it to be whatever I want. And I forgot to mention why I chose A. So let's go ahead and just work through it with if I choose B. So you noticed here when I chose A, the two rows that had the same value of A were next to each other. But now if I choose B, well, this is the row where B is 0, and this is the row where B is 0. And it starts to look a little bit complex. It starts to get kind of complicated to see what the equation needs to be, because you have to sort of look at these two rows that are not next to each other. So it's typically best to choose the inputs for your selector line so that you can easily identify which rows have a common value of A or whatever it may be. So I chose A because it tends to be the easiest, but you can choose literally whatever you want, right? As long as you properly figure out how these inputs need to be based off of what this input is, it'll be right. And you can do it using anything. Like you can start with B. So if I start with B here, then when B is 0, that corresponds to this row here and this row here, right? So let me just cross some stuff off here so you can see that. So now we've used B, so we want to ignore B. So we can see now that once I've actually crossed all this stuff out, we can see that Q is just whatever A is, right? So when A is 0, Q is 0. When A is 1, Q is 1. When B is 0, right? So here we can put A. And then in the other case, right, when A is 1, or B is 1, sorry, that corresponds to these two rows. So we'll ignore this one, and we'll ignore this one, and also we'll ignore B. And then you can see that, again, Q is just going to be whatever is just not A, because when A is 0, Q is 1, and when A is 1, Q is 0. So you would end up with not A here. This is also a valid answer. It's just a little bit harder to see because you sort of have to look at weird rows, and it's not very easy to see. Plus you have to sort of cross off a column in the middle, and you just end up, it ends up being a lot messier to do. But if you definitely can, and it's definitely not wrong. Let's see here. How do we draw this one as a circuit? So if I just do this here, there you go. That's the circuit. The point is that a mux is a component that you can use, right? You'll be making a mux first, but the second part of the lab, you'll just be using the built-in mux in circuit first, which, by the way, you should not be using to make the mux in the first part. You can just place a multiplexer, pass in whatever you want into it, and boom, you're done. That's the circuit, right? We're assuming here that someone's already made a multiplexer, and in this case, you'll have already made one as well. So in theory, you can just use the multiplexer whenever you want. And yeah, there is literally just a mux component in circuit first. I think it's under the plexers and decoders category. But yeah, it's literally just that simple, and that's sort of one of the main reasons to try to use these multiplexers, is that you can just go from table to circuit without any intermediary steps. Q being, yeah, I can do that. So someone's just asking for another quick little 2-input example, and then I'll go ahead and do a 3-input example. So let's say the output is here. So this is an AND gate. So now for here, again, I'm going to choose A because that tends to be easier, right? So when A is 0, we want to look at these two rows. So now, can anybody say what the equation for Q is in terms of B? Zero. Yeah. When I say in terms of B, right, the function doesn't necessarily have to have a B in it, right? If I can say, f of x is equal to 3, right? No matter what it's just a constant function. No matter what you pass in, the output's just going to be 3. There's no x here, but that's a valid function. And the same here. We can just say that Q is equal to 0 in this case, right? So for here, we'll just put a 0 for I0. Let me back up here. Okay. So yeah, we have a 0 right here. And for the second one, this is another case that you have that we just looked at. Q is just exactly the same thing as B whenever A is 1, so we can just put a B here. And that's it. That would be the one for AND. Technically, though, if you don't want to actually put a 0 here, and I would not recommend doing this on a test, just put a 0 here. That's way easier to think about conceptually. But the thing is that, like, sort of getting a 0 somewhere on a circuit is not... Okay, yeah. Oh, well, someone just asked, how do you get a 0 on circuit first? So, well, you can do something just like, yeah, you can just do B and not B. That's probably the easiest way to do it. Right? Because here, if B is 0, not B is going to be 1, 0 and 1 is 0, right? But if B is 1, not B will be 0, 1 and 0 is 0. So B and not B is just always equal to 0. So what you would just do is you'd put an AND gate, put not one of the inputs, and then connect B up to the NOT gate and the other input of the AND, and then the output of that would always be a 0. You can't leave it blank because that's not how circuits work. Technically, 0 isn't like no power. There's technically some amount of power that you need to send a 0, and there's some amount of power to send a 1. So nothing is not 0. Nothing is nothing. 0 is like 3.5 volts and 1 is 1. So you can't just leave a wire blank or like unconnected for it to be a 0. You have to put something there. You have to explicitly send a 0. So you'll have to use this B and not B trick. Or, as someone asked, could you use A? So in this situation here, if I pass an A here, in the case that A is 0, we want this to be 0, right? So, well, if A is 0 and we want this to be 0, then can't we also just, take the A input and pass it in over here, right? Because when A is 0, we want this to be 0. And the only time that this wire here is going to be selected is when A is 0. So this is sort of another way that you could sort of get around it. But we typically, like for implementation, if you want to do this to simplify things, you can. But yeah, on a test, just put on a test or quiz, just put 0. Because yeah, for your answer for the mux, it should just be clear and not too complicated. But yeah, that's just... If A happens to be 0 and you know it's going to be 0, for a test, you will not be using circuit verse. In the past, it's sort of been fill in the blank. So I think what it was is essentially we just had like boxes for S0, S1, or however many variables, and then boxes for I0 through whatever. And then you just had to put in what values you need to input there, or something like that. We try to avoid having you hand drawing anything because it can be complicated to actually get that submitted in some fashion. So typically we try to avoid you having to draw things, but you definitely can. There's likely going to be some sort of submission where you can submit your handwritten work, so that if that ends up, if you want to show your work on paper, which is typically how all of these tests are done, then you definitely can. But yeah, we try to find ways to get around it so that you don't have to do that. Any last little questions on this before I move on to a 3-input function? All right. Okay, so now we'll go ahead and take a look at a function with A, B, C as input, Q as output. And I'll just do, let's see. That. Okay, so now we're going to try to implement this with a 2-variable mux. We could do a 3-variable, but as I've said before, if we do have the 3-variable here, right? and we have S2, S1, S0, right? And with that, you know, you want to order these in this order here. You want S2 to be on the left. Otherwise, it's not correct. If we just pass in A, B, C here, then just for all the inputs, you know, you just pass in 0, 1, 1, 0, 0, 0, 1, 1, and you'd be done, right? It's really not all that complicated because the mux does pretty much all the work for you. But with the 2 variable mux, let me spread this out a little bit better. So S1, S0. And then we have I0, I1, I2, and I3, as well as Q. So the choice for the selector lines here is even more obvious. Let's just say I chose, I don't know, I'll just do something weird. Let's say I choose CA, actually, right? So now, for the 0, 0 case, that corresponds to this row and this row. The 0, 1 case corresponds to this row and this row. The 1, 0 case corresponds to this row and this row. And the 1, 1 case corresponds to this row and this row. That's just really hectic and confusing to look at. But if I choose instead AB here, then you actually end up with 0, 0 being here, 0, 1 being here, 1, 0 being here, and 1, 1 being here. Very nice and easy to look just straight down the list. So that's why I recommend doing that. It's easier for you. It's you're less likely to make a mistake if in trying to figure out where stuff is on the table. Plus, if you do it like this, what I would typically just do is just draw lines straight onto the truth table to just help divide everything up and make it easy to look at. Right, and I might even put something here, right? Because I've used AB, so really I can sort of ignore these, but I'll just leave it there for now. And again, just for your own sake, I'll go ahead and draw the truth table for Mux here. Okay, so now, again, we just go through the cases. So what happens when A, B is, let me use this. What happens when A and B are both 0? Well, that corresponds to these 2 first rows. So again, we've used A, B already, so we want to ignore those. And so we look at Q, and we see that Q is always the exact same thing as C. So we can just put a C here. So here, yeah, like with the 2 variable thing, we might put C here or something else, or 0 or 1, or even not C. But yeah, it's just more cases here. That's pretty much the only difference. So then we can look at, okay, well, what happens when it's 0, 1? Again, when it's 0, 1, we're selecting I1. So we want to put something in here such that the output here is the same thing as Q in this case right here. So here we can see that we have C. C is 0, but we want it to be a 1. And when C is 1, we want it to be a 0. So that means whatever we want the output here to be, it needs to be, we need to sort of input the opposite. So we can input not C here, right? So when C is 0, the Q output here will be 1. And when C is 1, the output Q will be 0. I do see someone typing something. Let's see if it's a question. Possibly not. I'll just keep going, and if I see the question, I'll answer it. Then we can go on to the next case when A is 1 and B is 0. That corresponds to, right, this is the number 2, so that corresponds to I2. Don't even need to look up at the table, just read binary, and that's the input that it corresponds to. So we want to put something here, such the output matches Q in this case. Well, here we can see that when A is 1 and B is 0, Q is always 0. So we can just put a 0 here, and that way the output will be correct. And then we can do the last 2 rows. That corresponds to when A is 1 and B is 1. And we can see that regardless of what C is, Q is always 1. So we can just pass in a 1 here. And we've successfully implemented Q. Any questions on this? All right. Well, in that case, let's see, what time is it? 10:05. Yeah, I can definitely go over one of those other examples with the K-maps because yeah, K-maps do take a little bit of time to get used to. So the more examples, the better. But this stuff, you pretty much just follow the same exact process, no matter what the size is. Just make sure you know how many variables you're supposed to be using. Like you might be given a 4-input function and asked to implement it with a 3-var mux, right? Or you might be asked to implement it with a 4-var mux, in which case it would be that just simple solution. Just take all of those inputs, pass them into the selectors, and then just correspond the I inputs to whatever you want the output to be, which is just literally going to be a 0 or 1 for every one of those. And for those of you who are a little bit more interested in, what size of the mux you actually need or something like that, I will, once I've finished this review, I'll post the document on Canvas that just sort of goes over a little bit more technical details. Sort of what I've explained already, but the sort of later parts of that document go into a little bit more complicated detail. Any last questions on this before I go ahead and move on to another K-map problem? Yes. So right now, essentially this was a 3-input function, and we implemented it with a 2-variable mux, right? And whenever you see a 2-var, that means there's 2 selector lines. And when you have two selector lines, well, how many binary numbers are there with 2 inputs, right? You could do 0, 0, 0, 1, 1, 0, 1, 1. There's 4 different options, so that means there's going to be 4 I inputs in a 2-var mux. Or really, if you have an n-var mux, it has 2 to the n I, like I whatever, ix inputs. And then n sx inputs. Well, there's 6 inputs here, right? If you're creating a mux here, there are all of these inputs, but then these are also inputs. We call these inputs. It's sort of a bad naming convention in that manner. I call them the data inputs, right? What I think, and I call these the selector inputs, but they're inputs either way. So you have right here, you have to take some sort of input for what you're selecting, but you also have to take in the data inputs. You have to take in all the possible options for your output in order to be able to output them. So a 2-variable mux has 6 total inputs. 4 of those are data inputs, and 2 of those are selector inputs. But in task 1, you're not going to be dealing with A, B, or C, right? Because you're just making a multiplexer. It's in task 2, once you're actually going to try to take a truth table and use a multiplexer to implement it, that you're actually going to be using A, B, and C. Yeah, the goal of task 1 is to make the multiplexer, right? None of this other stuff around here, right? You're just making this component. I believe you do have to create the circuit before importing it into the test bench. I mean, it has to be built so that it'll actually work, but I'm not sure. You might be able to import it early and then still edit it, but it's probably just best to just make the circuit and then make the test bench. Any last questions on this multiplexer stuff? And then I'll go ahead and do another K-map question. Yeah. Well, it's a 3-input function because it's A, B, and C, right? A, B, and C are the inputs. There's 3 of them, so it's a 3-input function. Right, typically, whenever you're doing a truth table, the stuff on the left are your inputs, and then the last column is going to be the output. Occasionally, later on in the course, we'll have multiple outputs, and we'll usually separate them by like a darker line. So there's these 3 inputs here. Well, the function itself has 3 inputs. A multiplexer has 4 data inputs, right? This right here is some arbitrary function. This is the circuit for that function. This is a multiplexer. It's important to make that distinction. This function here has this implementation, but this component and this component only is the multiplexer. Let's see. Is there a more complex form of multiplexer? It seems like I actually talk exactly about that, responding to Michael, that I talk about exactly that. Essentially, you can build a 2-var mux out of 3 1-var muxes in exactly the way that you're talking about. You can sort of do different layers, and you can compose them in more complicated ways. But yeah, if I'll send you that, or I'll post that document, and you can take a look, and that might help clear it up. But yes, you can sort of layer them in any sort of way. And yeah, if it's easier for you, feel free to unmute yourself and just ask the question. That's usually faster. Let's see, how can you draw the circuit of 2 variables of the input, but the output has 3 variables? So one circuit can't. Let's see. So any given circuit only has one output. You can technically have a circuit with multiple outputs, but that's really just multiple circuits packed into the same thing. In that task 0 of the lab, the things that appear in this Q column are also inputs, right? I have to give, in order for you to tell me what the output Q is, I have to give you A, B, and C. Or in this case, like in order for you to actually be able to tell me for any input of S1 and S0, I also have to tell you what I0, I1, I2, and I3 are in order for you to be able to tell me whether the output of the multiplexer is a 0 or a 1. I mean, if I tell you S1 and S0, you can tell me that, oh, Q is just whatever I0 is. But if I ask you, okay, well, is Q going to be a 0 or 1? I also have to tell you what I0 is, meaning it's an input. So Q is the only output. Everything else is an input. It's just you can sort of represent inputs just in this column by just, what you're essentially just saying is that you're going to take this input and then just output it to Q directly in this case. But for the circuit, I mean, for task 0 doesn't really require a circuit. You're not going to be really making anything. So that's just meant to be practice. In part 2, you'll be taking this table, making an equation out of it, and then making that circuit. Let's see here. So the question, if you didn't see it, is or comment is grasping this truth table and how it translates to the actual truth table of a 2-variable mux, or to this table, because these two tables are for 2 completely different functions. This is the truth table of a mux, and this is the truth table for some function. Right? They're not the same. They're not the same at all. They don't represent the same thing. Right? This mux here is this circuit here. It's the thing in the box. It's just this component. To implement this function here is all of this stuff, right? I'm going to take my A and B and C inputs and pass them into the mux in this particular way, such that the output Q here matches this column. Or was your question about trying to understand how this is the same thing as the truth table, like the full truth table for a mux? So you mean what I explained here, or like how this is the same, or how this translates, you know, to the larger truth table? Okay, perfect. Yeah, this is just I just wrote this down just so that you would remember how this component works. What do you mean make a circuit with I0 arrow I3? Sorry. So you mean make a circuit with those as inputs? I mean, yeah, like what you need to do is take this table here and go through that process that I explained, right? You sort of get the individual terms for each of these rows in a sort of more generalized way. So instead of just saying, oh, well, this term is S1 not S0 not, because that's what it is, you're also just going to end it with I0. And then if you just do that, sorry, I0, if you just, I'll put that as subscript, I0. So if you just do that for all the rows and then OR them together, that's an equation for a mux. And then you can just make that circuit. Right, and not all of these terms are going to have, you know, all 6 of these inputs, but that's fine, right? You don't need, it doesn't need to be like that. Okay. Any other questions about multiplexers? And definitely feel free to ask. Like it's important that you understand multiplexers. They're definitely bizarre if you've never come across them before. So. I do see someone typing, so I'll go ahead and wait for that. The mux table never changes. This is always and the only table for a multiplexer, or two variable multiplexer, I should say, right? You can yeah, so it's like an AND gate, right? You have an AND gate table, right, which you can write like this, right? And this never changes. This is always an AND gate, and this is always a mux. Any other questions? Okay, so let me quickly do something. And okay, so if you're comfortable with K-maps, you can just go ahead and go into your group voice channels and just start working on the lab. If you want to take a look at this last K-map example, then you can stay and look at it. Okay, so let's see, what is this table here? So we have A, B, space that out, and B, C, and then Z. Yeah, so just to comment, someone asked about Mux. Yeah, it's you know that truth table that I showed this right here, or S1 S0 Q 00011011. I'm assuming you're in. Yeah, you are. Okay. And then I0 I1, right? You can come up with the terms for each of these, S1 S0 not, and then I0, and then just do that for each of them and OR those together, and that's your equation. And then you just make that. And then from now on, once you make the mux, then you can just you're allowed to just use that mux component, which is a little bit bizarre to use, but it's not too bad. Okay, yeah, so I'll keep going. Let me scroll up to see the truth table. Okay, so and the outputs are 0, 1, 0, 1, 0, 0, 1, 1. So here I'll go ahead and put A, B, C. 0, 0, 1, 1, 1, 1, 0, 0, 1. And then, yeah, so now we can go ahead and just start putting things in. Again, I'm going to repeat myself because it's the most common mistake that people will make on like the first quiz or whatever. Make sure you order these in the right order. Otherwise, your K-map will be wrong. Okay, so now we can go ahead and translate. So we have a 1 here, 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 and here. Let's see, I'll mark that in gray. So we've got here, 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 and here. Okay, so now go ahead and start transferring over the values. So 0, 0, 1, 0, 0, 1, that's right here. Then 0, 1, 1, 0, 1, 1. Then we have 1, 1, 0, 1, 1, 0, and then 1, 1, 1 right here. This is actually a pretty good example of knowing what to circle and doing things in the right order. So again, we start first, seeing if we can circle any 8 things together, because that's the amount of boxes. Clearly there's not 8 ones here, so we can't do that. So then we'll go down to 4. Can we circle 4 ones in a rectangle? The answer is no. There are 4 ones, but we can't do any sort of circle like this. This is invalid because it's not a rectangle. And there's no possible way to do it for anyone. So we go down to 2. So now if we go down to 2, if we look at this one right here, we could either circle it right here, or we could either circle it right here. Because we have 2 options, I'm just going to ignore this one for now. The same thing goes for this one. For this one here, I could circle these 2 together, or I could circle these 2 together. And because of that, because I don't know which one of those would be better, I'm also going to ignore it. So then I'll go to this one here. This one can only be circled with this one here. So I will circle these 2 together. Right? Because otherwise, I'm going to be potentially wasting. Again, here we chose to ignore this one until the very end. So then we look at this one. This one can only be circled with this one here. So we'll actually circle these 2 together. And then we're done because every single one is in a circle. If you would have circled these 2 at the beginning, your solution would now be wrong because it would be more complicated than what it should be. So yeah, you want to make sure that you're only circling things that you know for sure should be circled or in the final solution. You don't really want to just start circling arbitrary things, because then you might circle too many things and end up with not fully minimized equation. Let me change this to blue here. Okay, so now this red equation here. This red equation here, we can see that it occupies this column, and this row. Here we see that A is always 0, so we can put a not A. And B changes, so we'll leave it out. C is always 1, so we can put a C. Then for this term right here, this is going to be this row, or this column, and then these 2 rows. So here, we can see that A is always 1, so we'll put an A in our term. B is always 1, so we'll put a B in our term. C changes, so we leave it out. And then our final equation is Q equals not A, C, or AB. Any questions on this and K-maps in general? All right. Well, if you have any particular questions past this point, just go ahead and send me a private message or something. And otherwise, you can just go ahead, go into the individual group voice chats and get started on the lab.